first of all, we talked about Stuart's fondness for this crazy way of detecting neutrinos by using an atomic bomb, and he always used to show this slide. So he loved this slide, especially I think the part with the foam and feathers and foam rubber to stop your detector from breaking on impact. So I want to share with you a few things during this talk. I'll talk a bit, I'll share a few things about what it was like to work for Stuart as a postdoc, because we didn't actually have a talk by one of Stuart's postdocs. And the first thing I remember about Stuart is, I met him in Panic in 2008, and I talked to him for a bit. And then I decided, well, I want to come and work for this guy, and so, getting hired by Stuart. This isn't the graduate student aptitude test. This is a different scheme. You spend, you're a grad student, you're graduating, and I was doing something completely different as a grad student, and you have to explain why you want to do this and what you're interested in. So you spend a couple of days agonizing and writing this long email about, I want to do this, and I think this could be interesting, and this, and then you get an email from Stuart. So average time 1.3 days, average time, and this is kind of indicative of a lot of my email conversation with Stuart. You have a long email and Stuart sends you a one-line reply, okay, do it. Now, I got here and Stuart was immediately latched onto the fact that I had spent quite a bit of time in the Israeli army. I think a lot of you have, or at least some of you have met Stuart with me and heard Stuart say things about me, so just to set the record straight, I did not at any point waterboard anybody. Right. So coming to the topic of this talk, I was asked to talk about searching for physics beyond the standard model at low energy. Now, of course, you can search for this at high energy, and you can search for things at the low energy frontier where kind of we all work. And really, schematically, this is really doing something like either if you're looking for directly at masses beyond the standard model, you're kind of looking for production of these particles, whereas if you're looking at the experimental scale, which is much lower than this, you're really looking for these tiny effects that come from what are basically loop diagrams and virtual particles in the low energy front. You could think that this is perhaps not as good a way to search for things. However, I did come across this recently, and that is what Freeman Dyson wrote, reviewing a paper about book by Wilczek. And out of 16 Nobel Prizes awarded, this is of course before the Higgs Nobel Prize, out of 16 Nobel Prizes, only a quarter were made on the energy frontier, while half of them were made on the accuracy frontier. So for making important discoveries, high accuracy was more useful than high energy, and this is really where Stuart excelled, I think. And particularly, I want to talk about the beta decay, or I was asked to talk about Stuart's beta decay experiments. Now, of course, you all know that in the beta decay, as far as we know, this is a V minus A interaction. And really, there is, in fact, no a priori reason for this. In fact, if you write out the most general form of the beta decay amplitude, you end up with 5 different, or actually 10 different coupling coefficients in there. And if you write out the beta decay Hamiltonian for this, you end up with this incredibly long Hamiltonian, out of which the standard model is really only a tiny part. So this is the standard model Hamiltonian, and this is anything that's not standard model is going to modify these, be it flavor mixing, left-right, right-handed currents, tensor currents, scalar currents, and this is all well and good. But you have Hamiltonian, but that does not actually tell you, because coupling coefficients are not observables. This does not actually tell you how to move to and do this in a lab. Now, luckily, people who are actually sitting in this room a while back had told us that if you look at the total decay rate for nuclear beta decay, you can write it out, and it has a whole bunch of coupling coefficients or correlation coefficients between, say, let me focus just on this one. This is a correlation coefficient between the direction of the emitted beta particle and the direction of the emitted neutrino. And that correlation coefficient really encodes within it all of the information about these extra couplings. Just to give you an idea of how this works, right? Assume you have in a Fermi decay where the beta and neutrino have to carry away no angular momentum. because they have opposite helicity, they are preferentially emitted in the same direction, and this gives you a correlation of 1, or preferentially they want to have a correlation of 1. In a gamma of Teller decay, of course, the exact opposite thing happens, and you have a negative correlation coefficient up to some factor that comes essentially from spin. And different nuclei have different combinations of these gamma of Teller and Fermi components. So of course, these will slice phase space in different directions. It doesn't, you don't actually only have to measure the small a coefficient. You can in fact measure many of these. I just put down all of the ones where you don't actually have to measure the spin in the final state. And this gives you a very clean and powerful way to access things, because these correlations can actually be measured to fairly high accuracy. Now, Stuart actually did this even before starting the latest program in Berkeley. Again, with people who are actually in this room, Stuart actually ran a Neon 19 experiment. I actually like this because I'm working on Neon 19 right now, so this is another way kind of my career in some sense is influenced by him. But of course, Stuart here immediately realized that there is a perfect setup in which to measure these correlation coefficients, and these are atomic traps. Now, why would you do this with atomic traps? Well, they're cold, they're dilute, so they have atoms are moving in there with low velocity. There's no angular smearing. It's dilute system. There's no interaction as the atom is leaving the sample. It's incredibly well localized, fractions of a millimeter, and it's highly isotope selective, so you have very little backgrounds. What's amazing to me when I started looking at this, these are the initial papers written on this. Stuart actually came up with this and started doing this less than 10 years after the topic of atomic traps was even started. And this I find amazing, the fact that, very indicative of Stuart, he immediately recognizes a useful, powerful technique and picks up on that to use that for something that could be completely different. It's very indicative of what we heard yesterday about realizing that, oh, there's this wonderful spectrometer around, so let's grab it and use it. So I don't really, because we're short on time, I really don't want to go into the mechanics of a trap, but suffice it to say that the idea is very simple and powerful. You take a bunch of lasers which are detuned off resonance towards the red, and then if atoms are moving towards that laser light, they will preferentially absorb the light from that laser and then re-emit it isotropically, and that gives you a dissipative force, and that slows everything down. The atoms lose energy, and this is called an optical molasses. And if you add in a magnetic field to give you some localization, this isn't a trap yet, you add in some magnetic field, and that gives you a very well localized system, and by proper selection of the angular momentum of the lasers, you in fact cause all of the atoms to be localized in the center. Now, this can't be done for all atoms. You have to have atoms with a specific level structure that we have. Well, this is the periodic table of the trappable elements. In fact, every year some more get added in there. Really, you can do this with the alkalis, the noble gases, alkali earths, and a few odds and ends around here, although I think I need to update this. There are some more by now. Now, Stuart immediately picked up on using sodium. And why do this on sodium? I think this also kind of follows Stuart's way of thinking. Well, firstly, stable sodium has been done. This is very well known. This is what Steve Chu did. And this was a very well-established technique at that point, although new, but still well-established. The other nice thing about his isotope of choice, which is sodium-21, it has the exact same level structure as stable sodium. And that means you can build your setup, do everything you need to do with stable sodium, table salt, or, well, not table salt, sodium iodide in this point, but do everything you need to do, and then all you have to do is slightly move your lasers by a small fraction of the frequency, and immediately you can trap with exactly the same way the radioactive sodium. And the other interesting point that you pick up on is it's actually fairly well known. So the theory predictions in this case are good to about 0.5%, because in these types of measurements, you always have to compare to the theory. Unless you have a theory to compare to, your measurement kind of doesn't make sense. But this, in fact, is a very well known, so you know the branching ratio very well, and you can calculate the standard model component. What's actually really nice about this, which I think is ingenious, is you don't actually need, so what the group here realized, you don't actually need to measure the angle of these two, this correlation between these two particles. In fact, all of the information gets encoded into the time of flight of the recoil ion. You do not even have to tag the emitted electron. That's actually really nice because that electron coming from the reaction has you end up with some energy dependence in it. And if you can avoid using it, you have a much cleaner measurement. In fact, what you end up using here is the shake-off electrons, which are electrons that are kicked off when an electron that is in a sodium surrounding a sodium nucleus suddenly finds itself around a neon nucleus, impulse approximation, some of them get kicked off, and that gives you a completely uncorrelated start signal, which is uncorrelated with the nuclear decay itself. In fact, basically what happens if you have the beta and the electron emitted in the same direction, you will have high recoil momentum, and exactly the opposite in the other way. And then basically what you do is you simulate your system well enough for your experimental conditions, and you calculate the expected time of flight for example, 2 different values of this correlation coefficient. You take a measurement and you basically perform essentially a 1-parameter fit to the measured time of flight histogram. Now this is a really, really, really fantastic apparatus that was built here. It's incredibly, it's wonderful. You have a proton beam producing sodium-21. It's a p-alpha reaction. They diffuse into your atomic, the atomic beam, the atomic atom trap. 6 laser beams, another beam to slow things down, and a bunch of detectors around it. Now this of course looks nice on paper, but we're experimentalists and we all know that things look a bit messier in reality. When I show this picture to my atomic, to the people I work with who do AMO, they're always incredibly surprised. All of the people who do atom traps tend to have these really small, tiny glass cells where they have, say, rubidium traps. And then I point out this to them and say, well, this is our trap. This is our trap. Of course, you need a big trap because you need the time of flight. But they're always surprised by this. And what I think is maybe one of the most wonderful pictures I've seen in physics is this. You end up with this. And this is fantastic to me that you can actually see with your naked eye a bunch of atoms. So this is my recruitment poster for students. Here, I will show you atoms in free space. Now, as Stuart was going towards this wonderful measurement of the beta neutrino correlation, there were, of course, rather notable results along the way. This was the world's first trap for radioactive atoms. Of course, Lou is sitting here and knows all about this. This is also the first microwave transition measured in a radioactive atom, which is, again, I think fantastic. And you know, this is a long process, but finally you do end up with a measurement, and the first measurement, that 2003 measurement, you actually end up with a result that is about 3 standard deviations from the standard model. Now, of course, Stuart being Stuart, I'm sure Paul can tell us a lot more about this. I'm sure he was not pleased with this result or unwilling to accept it before examining all of the other possibilities. And in fact, it does turn out that there is a population dependence. So the more atoms you have in the trap, the lower this value that you measure becomes. And that is, again, very indicative of Stuart's way of doing things. You don't let up. You don't grab the first result that you would like to see, because of course everybody would like to see deviation from the standard model, but rather you destruct test it. And in this case, you destruct test it to oblivion because this is not a true measurement. It actually turns out that in this case, this has to do with the formation of neon dimers in the trap, where one of the dimers undergoes radioactive decay and scatters off the internuclear potential. And this reduces the observed value, and what you end up doing is you extrapolate to 0. So you do this measurement with several different values, several different numbers of atoms in this trap, extrapolate to 0, and when you do this, you do in fact end up with the standard model value, as I'll show you in a minute. Now, again, in one of those brilliant ideas of taking something that seems a problem and using it to your advantage, you actually realize that this formation of dimers and photoionization of dimers provides you with a perfect way to calibrate your system, because you ionize a dimer and you get basically a shake-off electron and an ion or a molecular ion that flies off, and you know exactly where things started, and this has nothing to do with nuclear decay, so you can calibrate your optics and your time of flight perfectly. And in fact, you can do this amazingly well. Now, once you've done and solved all of these, you can come up with the standard, with the measured beta neutrino correlation, and you end up with an answer that is exactly, let's see, I think this is the standard model times this is the fraction of the answer in the standard model, and you come up with an answer that is exactly corresponds to the standard model. This being a measuring nothing workshop, I couldn't resist rewriting this answer as the differential change from the standard model, just so that I could get a value of nothing, right? So in fact, this is once again, a measurement of nothing, but a very, very precise nothing. Now, you can actually, there are many different ways to show this result and to plot this result in various different configurations. You can see that this is, I guess, a bit out of date plot by now, but you can see that this sodium-21 result from Berkeley is still one of the world's best. And depending on which way you prefer to plot things, you can get different projections of this. Now, one of the great things about Stuart was very inspiring, and I think there's one of the ways that you can see this beautifully is if you just make an incomplete, I know, list of the experiments that are doing the same thing and are looking at different atomic or nuclear systems. And this is an incomplete list of the things that are being done. And you can see that Stuart has left us with an impressive legacy of the experiments, of experiments that are all pursuing this idea of using traps to do extremely high precision measurements. Now, there are two last stories I want to share before I let you go and get your coffee. And so one of them is and this, Tom reminded me about this last night. I had completely blocked it, I guess. When I was a postdoc here, we were working on building the ion trap, and I was at the 88 high bay walking out with a vacuum chamber when I slipped and hit my head on a pallet lifter over there. So, and I drive up to the 88 health office, get stitches. I call Stuart and say, Stuart, I'm getting stitches. He says, well, what happened? I said, well, I was an idiot. Stuart accepts the answer, but that's not good enough for the H&S report. And this, in LBL parlance, this is called a reportable incident. So Stuart really hated doing paperwork, as you all know. So in penance for my blunder, my penance was doing the paperwork. And I actually I dug up the old the old plots, the old part of the old report Stuart made me write. I tried to make it very detailed. I actually was hoping to drown them in details so that they will leave me alone. Didn't work. And the other story that I have to share with you, I told Joyce I would share this yesterday. Or I told Joyce yesterday I would share this. When I got to Berkeley, a couple of months after I got to Berkeley, the 88, we were switching offices and they're doing some, ordering new furniture for the offices. And, Stuart decided, or we sat down together, we figured out what furniture we want, and we requisitioned furniture, and the furniture doesn't show up. And it doesn't show up for a while. And I actually looked at my email list, and I don't know if you can see this, but the first email about this is from November, and then it goes all the way down to February, and Stuart was getting progressively more and more annoyed because he really couldn't figure out what was taking so long to get a bunch of tables. So this is actually the email I'm going to show now, and at some point Stuart comes into the office I was using, hands me a textbook, says, "Follow me." So I walk over to the next office with him, or to the office I was supposed to occupy when the furniture would eventually show up. He gives me the textbook, tells me, sit down on the floor, pulls out his iPhone, and takes a picture. And then the next day, I get this email from him. I don't know if you can see this, but this says, "Hi, Diana. This has really involved a large number of people. It's also taken a really long time, but thanks for the help. I thought everyone would enjoy seeing Dr. Ron working in his office." And guess what? 2 days later, I had new furniture. So I think this exemplifies Stuart's unique way of dealing with bureaucracy, cutting to the chase and getting things done. And finally, about 2 years ago, I had the incredibly good fortune of having Stuart and Joyce over in Israel for 2 months visiting us. And it was a tremendous experience, both for me and for my students, because we gave a class together, and it was fantastic. And Stuart has been a tremendous influence on me and on my career, and I can't walk into my lab without thinking about him and without thinking about what he would do, and it's really, I think he has been one of the most influential people I have ever met, and I miss him dearly every day, and I'm grateful that I had the opportunity to work with him and know him. So thank you.